Hello everyone. In this last day, I'm going to give more applications more geometric application of the use of spin-C geometry, and I'm going to finish by giving some outlines of my research work and idea, or what are the ideas that I'm interested in. So I'm going to start today with another application. So if you remember yesterday, we have established or proved the Friedrich-Spinorial characterization of surfaces into R3. And so surfaces into R3 are characterized by having a spin structures carrying a spinor field satisfying the Dirac equation. And the idea was I have on R3 a parallel spinor, and then I restrict the parallel spinor. So today I'm going to talk about a spin-C application, and not spin this time. So I'm going to talk a little bit about Riemannian, homogeneous Riemannian manifolds. So what are the simply connected homogeneous manifold of dimension 3. We already know a complete classification of simply connected homogeneous manifolds of dimension 3. First of all, we have space form. So we have R3, the sphere of dimension 3, and the hyperbolic space of dimension 3. We have the solvable group SOL. And we have a last type of, or the last part of the classification are those denoted by E kappa tau. So what are these E kappa tau, and what are kappa and tau? So if I'm going to write it clearly here. So if tau is 0, and if tau is not 0, so tau in fact it measures the defect to be a product or not. So when tau is 0, this is I have S2 of curvature K times R, or kappa, times R, or I have the hyperbolic space of curvature kappa times R. And when tau is not 0, I have the Berger sphere, the Heisenberg group, and I have the universal cover of the Lie group PSL2R. This corresponds to the case when kappa is negative, here when kappa is 0, and here where kappa is positive. So these are the complete classification of homogeneous manifolds of dimension 3. So today I'm going to consider or surfaces of E kappa tau. So when I say from now on E kappa tau, I mean the following two products, or Berger sphere, the Heisenberg group, and the universal cover of PSL2R. So next proposition, this was a result obtained by Julien Roth and myself. So proposition, Nakad and Roth, and you have a surface and two isometrically immersed in E kappa tau of mean curvature H. This is spinorially characterized by having on M2 a spin-C structure carrying a spinor field phi of constant norm satisfying a Dirac type equation given by dm phi h phi minus etal phi bar. I'm going to say what is phi bar in 1 minute, and the curvature of the auxiliary line bundle defining this spin-C structure in any local orthonormal frame E1, E2 is given by minus I kappa minus 4 tau squared is phi bar over norm of phi squared. Where phi bar here, because I'm on dimension 2, we said that we can split the spinor bundle into the positive spinors and negative spinors. So by phi bar I mean the positive part of phi minus the negative part of phi. This comes from the decomposition of phi into phi plus phi minus. So a complete spinorial characterization of surfaces in E kappa tau is to have a spin-C structure with a special spinor field. What I mean by a special spinor field, it satisfies some type of a Dirac equation, dm phi h phi minus I tau phi bar, and I have a control on the curvature of the auxiliary line bundle defining the spin-C structures on N2. I'm not going to give you the full proof, but the idea of the proof is the following. Idea of the sketch of the proof. So again, E kappa tau, if tau is 0, then you have S2 times R and H2 times R. And when tau is not 0, you have the Berger sphere, the Heisenberg group, and the double cover of PSL2R. Okay, one can prove that S2 times R and H2 by R are spin C with parallel spinor. And when tau is not 0, Berger sphere, the Heisenberg group, and PSL2R, the universal cover, are spin C with killing spinors. So one can restrict this. For example, if you take the case of S2 times R, you take the parallel spinors and automatically restrict. You get a spinor field that satisfies the Dirac equation, d phi equal h phi, but there is no expression in tau because tau is 0. Then you calculate the curvature and you get the good term or the good expression of the curvature. In a similar way, you can restrict a killing spinor, and then to find, using the relation between both Dirac operator on my ambient manifold on the hypersurface, you can get the modified Dirac equation. But what are the beautiful and the geometric application of this result of the spinorial characterization of surfaces into E kappa tau is the following. Corollary. So also by Nakad and Roth in 2011. A Lawson type correspondence so simply connected surfaces minimal in the Heisenberg group are isometric, or if you want, every simply connected surface minimal in the Heisenberg group is isometric to a simply connected surface in H2 times R of constant mean curvature half. So this type of Lawson correspondence has been proved already by Benoit Daniel, but of course without using spinors. Here we got a spinorial characterization, or a spinorial beautiful geometric application, a spinorial proof of the Lawson type correspondence. So you can go from a surfaces from a minimal surface in the Heisenberg group. In the Heisenberg group, yes, and then to get a new or an isometric surface in H2 times R of constant mean curvature 1. Of course, again, this can be done for for all. This correspondence can be proved for any manifold E kappa tau, Berger sphere, the Heisenberg group S2 times R, but here I'm specifying it only for the Heisenberg group and H2 by R. But if people interested can check the paper, my paper with Roth, where we establish or we give the spinorial proof of this correspondence between simply connected surface in E kappa tau for any kappa and any tau, not only for the Heisenberg group and H2 times R. Just to mention that this is a spin-C proof, even though Berger sphere, the Heisenberg group, the PSL2R, S2 times R, H2 by R, all of them are already spin manifold. By using spin geometry, you cannot characterize or surfaces spinorially, because even though these are spin manifold, but they do not carry special spinor fields. So but when I construct a spin-C structure on them with beautiful or easy to deal with spinor field like para and killing, then the restriction becomes easy. So the idea of this Lawson type correspondence is the following. So sketch of the proof. So if you have a manifold of a surface isometrically immersed into H2 times R, which is E, kappa is -1 and tau is 0, of mean curvature, of constant mean curvature half, this is spinorially equivalent to say that M2 is spin-C carrying a spinor field of constant norm and satisfying the following Dirac equation: dm phi half phi, and the connection of the auxiliary line bundle, replacing by kappa -1 and tau 0, you get I phi bar norm of phi squared. So I'm going to call this one system 1. And now what does it mean spinorially that you have a surface isometrically immersed into the Heisenberg group, which is E, kappa is 0 and tau is half of mean curvature minimal, so of constant mean curvature. This is spinorially equivalent to M2 spin-C carrying a spinor field that's called the psi of constant norm, satisfying the Dirac equation dm psi minus half psi bar after replacing kappa by 0 and tau by half, and the connection on the auxiliary line bundle is given by I psi bar over norm of psi squared. So to get this Lawson, if I call this one system 2, to get the Lawson correspondence, so in order to get that the correspondence between minimal surface into the Heisenberg group and the surface in H2 times R of constant mean curvature half, we have to prove that both systems 1 and 2 are equivalent. So how we will prove that system 1 and 2 are equivalent? If you assume that system 1 is satisfied, so define psi to be phi plus I phi minus. So the system 1 is defined for phi, then I define a new spinor psi, and psi satisfies system 2. And for the converse, assume that you have system 2, so you have a spinor field psi satisfying the good equation, then define phi to be psi plus I, psi minus also. So, and then phi satisfies system 1. So I can go from system 1 to system 2, then from system 2 to system 1. This means that I have a Lawson type correspondence between minimal surface in the Heisenberg group and constant mean curvature half surfaces in H2 times R. So I'm going to finish today with my last part, in which I'm going to state or give an outline of the importance of spin-C geometry to get geometric results and topological results on manifold and their hypersurfaces, and why I'm personally interested in studying deeply these structures on on any type of manifolds, as well as their submanifolds and hypersurfaces. So other applications So I was able also with Julien Roth to prove that using spin-C geometry, E kappa tau can be isometrically immersed in CP2 of some constant holomorphic sectional curvature. So we use spinors on E kappa tau to construct such an isometric immersion. We were able to prove that there is no totally umbilical surfaces in E kappa tau and some E kappa tau. So as you can see, all these geometric results, or all these results, are purely geometric. There is no spinors here, but however, we use the spin-C structures on E kappa tau, for example, and here also, to prove that no totally umbilic surfaces, or to prove that we can isometrically immerse E kappa tau in some CP2. When I say some CP2, I mean of constant holomorphic sectional curvature, not necessarily 4 or 1, but some other constant. Other application also in this direction was also with Julien Roth. We were able to characterize spinorially surfaces into CP2. So here it's not anymore a hypersurface, but it is a submanifold of codimension 2. So the normal bundle here is of rank 2. It's not trivial anymore. But however, we were able to restrict some Kählerian killing spinors because CP2 is scalar. And these spinors are spin-C and not spin, of course, because we know that CP2 is spin-C but not spin. So by restricting these Kählerian killing spinors to any surface M2, we were able to get a spinorial characterization of surfaces, to be more precise, of complex and Lagrangian surfaces in CP2. Another application also, this result has been established with Nadine Grosse from the University of Freiburg in Germany. So what we did, we studied boundary value problems for the Dirac operator on spin-C manifold, but of bounded geometry and with non-compact boundary. And this generalizes a part the theory of boundary value problem by Christian Baer and Werner Ballmann for complete manifold with closed boundary. And as an application, we derive the lower bound of Ijazi, Montiel, and Dong involving the mean curvature of the boundary for the spectrum of the Dirac operator on the non-compact boundary of a spin-C manifold. So more precisely, we prove the following. So you have a Riemannian manifold of dimension n plus 1, complete spin C with boundary, and we denote by L the auxiliary line bundle as usual. We assume that M and the boundary and the auxiliary line bundle are of bounded geometry. So the curvature are bounded. So what do I mean by the curvature is bounded? I mean the curvature tensor of M and all its covariant derivative are bounded. The injectivity radius of sigma is positive. There is a collar around sigma. The injectivity radius is greater than some epsilon in some neighborhood, and the mean curvature and all its covariant derivative are bounded. This is the terminology of bounded geometry. Then we have before we still have one more condition. We assume that the mean curvature is positive, and we assume some coercivity condition of the Dirac operator. I'm not going to go into details, but here, because my manifold is not complete and I'm of bounded geometry, I should assume moreover that the scalar curvature plus I omega is a non-negative operator, and of course one more time that the Dirac operator D is B plus coercive at infinity. Then the first eigenvalue of the Dirac operator on my boundary is greater or equal to n over 2, the infimum of the mean curvature. Of course, this has been proved for the compact case by Ijazi, Montiel, and Dong. Of course, the equality case is characterized when lambda 1 is positive. It's characterized by the mean curvature is constant, and any eigenspinors corresponding or associated with lambda 1 is the restriction of a parallel spin C spinor on my ambient manifold. So these are some application of the use of spin C geometry. You can check my webpage nakadroger.com, where you can see all what we did with many authors, with Michaela Pilka, George Habib, Fida Shemi, Nadine Grosse, and many other, with Rafael Herrera, etc., and with many others on the use or the geometric application of spin C geometry and spin geometry more precisely as well. Thank you.